In this lecture, we'll learn how to write assembly code for recursive functions. A recursive function is one example of a non-leaf procedure function. A non-leaf procedure function is a function that may call other functions. The procedure to call other procedures is for nested calls. The caller needs to save on the stack the return address registers and any callee saved registers that it may call, and it must restore at the end of the function the values that were saved in the stack that are needed after the function call is executed. A classical example of a function that calls itself is the factorial function. The factorial function is implemented as follows. The factorial of n, if n is less than 1, is 1, and otherwise it's equal to n times the factorial of n minus 1. We'll use this opportunity to illustrate a step-by-step creation of an assembly function from a C function. I will be slowly lowering the representation of the function until I get close enough to the assembly code that is very easy to write the assembly code. So let's start with the code for the factorial function that's given on the top of the slide. And let's start lowering this representation. So because this function is a recursive function, the first thing that I need to do is to save the value of the return address register. Next, I will be reproducing the code that I have there, but if I will return from the function, I need to restore the value of the return address register, and then return the value that I should return. In this case is 1. And if n is not less than 1, I need to compute the value of n times the factorial of n minus 1, and then I need to restore the return address register and then return that value. So the main point of this first transformation is that before I start execution of the function, I must save the value of array, and I must restore the value of array prior to returning to the function, no matter how many returns I have. How do I return 1? Remember that in RISC-V, the return value is always in a 0. Therefore, to return the value of 1, what I have to do is to write the value of 1 into a 0 and then return a 0. To compute the factorial of n minus 1, I need to first compute the value of n minus 1, which, let me get out of the way here, which I will put into A0, because A0 is also not only the return value, it is also the first argument of any function in RISC-V. Now, how do I obtain the value of factorial of A0? The factorial of A0 actually returns in A0. So the factorial of n minus 1 will be computed. The value at the end of the computation will be in A0. So saying that I obtain the value of factorial of A0 is equivalent to say that I obtain the value of factorial of A0 and I write the value into A0. So now I replace that expression by A0 into the multiplication expression. But n is also n is also A0 in A0 because n is also the argument for the function itself. And n is used in the multiplication. So I need to do something about that. And what I will do is I will save A0 in the beginning of the function. And when I restore array, I will also restore A0. This way, the original value of n is preserved before I change the value of A0 to do the call for factorial of n minus 1. So that has sorted that problem. And now I can then replace n by A0 in my code. But there is something wrong with this code. Let's see what could be wrong with this code. what's happening here is that, let's say that this function was computing the factorial of 3. So if this function was computing the factorial of 3, in the very beginning of the function, I have saved the value 3, that's the current value of A0, into the stack. And then I have proceeded with the computing of the function, so 3 is not less than 1. I go into the else part of the computation. Now I subtract 1 from 3, I get 2. I call the factorial of 2. I receive the value of the factorial of 2 will be in A0 after that computation. And then I restore the value of A0. When I restore the value of A0, I am restoring the 3. So when I do the multiplication, I'm multiplying 3 by 3 instead of multiplying 3 by the factorial of 3 minus 1. To fix that, so this is what is wrong. This multiplication is n times n, and what I need to compute is n times the factorial of n minus 1. To fix that, I will copy the value of A0 into a temporary prior to restoring it, and then after restoring it, I will multiply the restored value of A0, which is n, by T0 that contains the value of the factorial of n minus 1. Now we need to deal with the saving and restoring of these values and replace them by lower level statements. Well, we know how to do that. We know that to save 2 values into the stack, we need to add -8 to the stack, and then we can save. And here I'm using a notation. I'm introducing this notation now, but we will see in several other lectures, where I'm using the value m sp plus 4 mmsp. This is representing memory. What I mean with that is the memory whose address is sp plus 4, the memory whose address is sp. So notice that I wrote the value of RA and A0 into the memory when I first entered the function. And prior to when I had the restore statement in the lower part of the function, I am now reading from the memory first and then restoring the value of sp. There is another restore statement where I should be restoring the value of array and A0. However, if I analyze this code, I haven't done anything other than testing the value of A0 when I get to that point. Therefore, I do not need to do anything to restore the values because the values have not changed. I have, however, to move the stack pointer back to where it should be. Therefore, that restore statement can be replaced by simply sp receives the value of sp plus 8. So now that I have this code that is a very low level, it's very easy to replace this code with assembly code. First, the saving of the values consists in subtracting 8 from the stack pointer and doing 2 store word operations. Next, I have a test. The test in my pseudocode is asking whether A0 is less than 1. In the assembly, I'll be asking whether A0 is greater or equal than 1, because I'm asking whether I should jump over the code, the body of the if. Now I will add 1 to, I will make A0 equal 1, and I'm gonna add 8 to sp so that I am ready to return, and return A0 is the jump and link return statement where I use the value of array into the statement. If I have returned from that point, I'm done. If I have not returned from that point, I need to now go to the place where I would go from the conditional, that's the else of the loop. I add -1 to A0, and then I will jump and link to the factorial. This is the function call. The function factorial is calling itself. Then I will copy the value of A0 into T0, and I will now do the restoring of the values of A0 and RA, move the stack pointer to the right position, perform the multiplication, and returning from the factorial function. So this is how I generated the code for this recursive procedure. What we have done in this part of the lecture is to show how I can step by step change the representation of the function to lower it until I am at a level that is close enough to assembly that I can write the assembly code. In the second part of the lecture, we'll simulate the execution of this function and illustrate what actually happens in a recursion.